Hello, everyone. This is Billy Younger for Physics Solutions, and I'm writing or recording a video on how to apply Ampere's law for a non-calculus based physics course. In other words, for what we call college physics or algebra-based physics, or even introductory physics, which actually there's a lower level too, where you just say lower in terms of how much math you need, which is called a conceptual physics or something like that. I'm actually just using this so you'll understand where the results came from. I'm not using this to mean that the student in that class should be able to come up with these results. I'm just trying to show you how they come about. What we're going to be discussing is called Ampere's law. And what Ampere's law says is if you take and like consider a closed loop, let's say like a circle or maybe even the outline of a leaf lying flat like that, but it actually has to start and end on the same point. So it's actually a closed loop. If you take and break that closed loop up into little segments delta L, and then find the part of a magnetic field that's parallel to that and multiply that times that little delta L, the strength of that magnetic field in Tesla, times the length of that little field, little length, that would be in meters. Then you do that all the way around the closed loop. According to Ampere's law, your result will be equal to some constant, which we call the permeability of free space, which is 4 pi times 10 to the negative 7th Tesla meters per amp. And then also times that mu zero, or that constant, is the total enclosed current. And there's kind of a little rule about that. Basically, if you imagine the little closed loop you're going through is like this, say, then I take my right hand and say, okay, well, it was going this way with my right hand, it went around like this. Now, if I'm curling my hands this way, if the current is actually parallel to my thumb when I do that, then that's a positive current. If it's pointing the other way through that loop, then it's a negative current. So that's what we got to use. So I'm going to first off take and write, well, the law is already written on the thing I'm going to share with you, and the constant's already written as well. The permeability to free space is called mu sub zero. And what I'm going to do is interpret that formula and then show you how to use it on a wire. So let me go ahead and share my screen. Again, this is Ampere's law for college physics. I'm going to try to share my screen with you now. Okay, so as you can see, I already have Ampere's law written up there, and that sigma, that capital E looking thing, is the Greek uppercase sigma, and it just means sum up all of the parts. So we're going to imagine a closed loop, and we're going to basically break it up into small segments, delta L, and then we're going to measure the magnetic field near that delta L, and we're going to multiply the magnetic field strength that's near that delta L and is parallel to that delta L. We're going to multiply that by delta L, and then we're going to go to the next one and go to the next one and go to the next one and go to the next one until you're all done. When you're done with that, your total sum will be equal to mu zero times the current enclosed. So let me show you how we're going to go about doing that. Let me first, I realize that what we have discovered is that a current carrying wire will create a magnetic field. And if you were to grab that current carrying wire with your right hand, notice I keep saying right hand, everything's got to be done with your right hand. But if you grab that current carrying wire with your right hand, not unlike I'm holding this pen right now or the stylus right now, and your thumb points in the direction that the current's going, then your fingers curl around the wire in the same direction that the magnetic field points around the wire. Not only that, what we've discovered is that the magnetic field strength is a constant as long as you stay on a circle of fixed radius and that is centered on the center of the wire. So you imagine the wire, which of course is really, really, really long. There's an axis of symmetry where you can rotate that little wire around and around and around. That center axis is called the axis of symmetry. Now, if you imagine a circle perpendicular to that line, so that it actually is like going right through the middle of, let's say, a bubble sheet made out of that circle, then what you have is a loop that's concentric with the center of the wire. So let me show you an example. I'm going to first draw the concentric loop because it's easier to do it before the fact. So here's my concentric loop. I'm going to draw it in blue, and I'm drawing it concentric because I know if it's concentric, then automatically the magnetic field for this wire that I'm getting ready to draw will be a constant all the way through it. So here's the magnetic field, or here's the current carrying wire that I'm drawing. And we're actually imagining this is very, very small, but going right along the center. And in fact, if you imagine a plane created by that circular disc there, then the wire would actually be perpendicular to that. We're going to say, in fact, that this is consistent with the right-hand rule, so that the current in the wire is actually going upward. So that's the current I. Now, when we do that, what that means is now this is consistent with my right-hand rule if I do my B delta L in this direction, meaning in front of the wire, it's going to go to my right. Behind the wire, it's going to go to my left. To the right of the wire, it's going into the page, and to the left of the wire, it's coming out of the page. So that direction is the direction of magnetic field point. And since this circle is actually centered on the axis of the wire, you know that the magnetic field will be a constant all the way across that. So when I go to add up the summation of the components parallel of B times delta L, what you see is all the magnetic field is completely parallel with the circuit. So you can imagine the basic length around the whole thing is going to be multiplied ultimately by the magnetic field strength, which is a constant. So in other words, each little part, let's say we imagine this little section right here, right there, we're going to have a magnetic field that is parallel to it and has a magnitude B parallel. And right there, we're going to have a little delta L. And that's the length of it. And if I go to somewhere else, it's going to be the exact same thing. So since this magnetic field is a constant on every delta L, then I can go ahead and say, pull the B out in front. In other words, factor it out, and I get B, which again, is just B. It's automatically parallel, so I don't have to do anything. And then it's going to be delta L1 plus delta L2 plus ... until you get up to delta L, let's say, N. However many N we break that circle up into, we know that the sum of the little delta L's is going to add up to the circumference of a circle. So ultimately now I've got B times 2 pi r, where r is this radius of this Amperian loop, and that's what we call that thing, is an Amperian loop. So the left-hand side of Ampere's law just gives us B times 2 pi r. Now, notice that current is actually going exactly perpendicular to the plane made by that circle. And in fact, it's consistent with the right-hand rule. So the right-hand side, which is mu 0 I enclosed for this case, just happens to equal mu 0 times I. Okay, again, I'm going around the loop in this direction like my fingers are showing right now, and the current is going straight up. So it's consistent with the right-hand rule, so it's a positive current. And this is the right-hand side. So because of that, we can set those two equal, and I get B times 2 pi r is equal to mu 0 I enclosed, or actually just plain I now, since we've already figured out exactly what the I was. So now what I say is the magnetic field due to a current carrying wire is given by B equals mu 0 I over 2 pi r. And that's our formula. So we can use this to calculate the magnetic field in Tesla for any distance r away from the central axis of the wire. And we're going on the assumption that basically the wire is infinitely long. So in principle, what you're thinking is the wire goes for infinity this way and for infinity this way. Now, there's no such thing as an infinitely long wire, of course, but in the physics world, if we're talking about a distance r away from the center of the wire, that's at least a factor of 10 smaller than the distance to the end, then we're starting to approach infinity. If we go all the way up to a factor of 100, then we're really getting close, and 1,000 even more, so on and so forth. So if you take a 3-meter wire and you're 3 centimeters away from it, you're really just 1/100th of the distance from the end. So that's more or less an infinite wire for mathematical reasons. In other words, we're not going to enough decimal places for it to make any difference. So that's one result we can get. There's another result we can get, though. This one's for a current carrying wire, and that's now an equation you can use. But there's also one for a solenoid. Now, you might not know what a solenoid is, but I'm certain you've seen them before, and you probably even made one in grade school. So what's a solenoid? So a solenoid is probably what you remember making in school, or seeing someone make in school, or seeing a picture of in school, which is an electromagnet. So what you would do is you take like an iron rod or something, and you wrap wire around the iron rod over and over and over again, and then you slip the iron rod out and you're just left with a tube of wire. That's all you need to make a solenoid. You don't have to have the rod in there. You can put a rod in there if you want to. That'll make other things happen. But the main thing is we're just thinking about a coil of wire that looks something like this. And we're looking at it from the side, so I don't really see much except the curls themselves. But we know what's actually going on is when you go from one curl on the left to the curl on the right, then you come down to the next curl, so on and so forth. So it looks like that. Now, if we were to cut that in half, what we'd see, and let me go ahead and do this. I'm going to call this the last one. It's not very many turns for a solenoid, but we'll do it like that. So we're seeing the current, in fact, is coming in this wire. And if we cut this in half, at least in our imagination, what we'd see is down here at the bottom, the current is coming towards me, and towards me, and towards me, and towards me, and towards me, like that. And that's about equal to the same number of turns there. Now that current will, of course, go back and then actually come to the forward because it came towards me, and then go in to a wire here. And in fact, it would look like I've actually drawn the arrows backwards. Those arrows are supposed to be going into the page. So it's more like the current at the bottom is going into the page, and the current at the top is going out of the page, because that looks like the tip, the nose of an arrow, if you will. So that's what a solenoid is supposed to look like. Is just basically a series of wires that cross over like this from one ring to the next. And then this one, of course, is the one that would go like this and then come back down, say, and the current comes out of it. And this, of course, would be the one that goes like this out in front, and the current comes in it. Okay. So if you actually know now that that's what a solenoid is, you can sort of think of it and figure out, or I can teach you basically what the magnetic field lines look like. So let's imagine we have a bunch of those little wires, dot, 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 all of them coming out of the page. And it goes really, really long, say, and then we've got a bunch more wires that are actually the same wires, only these are going into the page, dot, dot, dot. Like that. These are dots in the center, so they'll come out. We can imagine what the magnetic field lines will be like, and in fact, they'll look like this. They make a very strong, uniform magnetic field in the coil. And the strongest part would be dead center in the coil, but it's all pretty much the same strength everywhere, like that. And then they come out, because magnetic field lines never end, they always close. They come out like that, and they come out like this. Okay, so magnetic field lines are pointing like this out here, and this out here, and of course this out here, this out here, and this out here. So those are your actual magnetic field lines. So if I choose to use Ampere's law, if I make one of my lines on my Amperian loop, which I'm going to make as blue, if I make one of those lines go this way, then the magnetic field is going to be basically straight, parallel to that section of wire. So I will do that by showing this part right here. Okay. And then I'm going to take a cut and go straight up. Well, actually, let me move this a little bit so that one's easier to see too. So there's part of my Amperian loop. And now I'm going to go straight up right here and straight up right here and then straight across right here. Okay. Now I want to go the same direction of the magnetic field, so I need to go around the loop in this direction as shown. So when I do that, then the left-hand side which is the summation of B parallel to delta L, okay? Basically, this side right here, if I call this length L and I call this distance A, then I get the magnetic field strength inside B times L for that first part, and that's the bottom arm of that circle. And then as I go right between these wires, the magnetic field from one wire, say right here, that's going to point this direction between, because it goes around in that direction like that. And then the one next to it also has a current coming the same way. So in fact, that magnetic field is going this way as well. So you see between the magnetic field is 0. And then when you get higher up, let's say along this area, B is approximately 0 for all this out here, just because it's so weak compared to the magnetic field inside. So I get plus 0 plus 0 plus 0. That's what my left-hand side of Ampere's law gives me. It gives me B times just L. Now the right-hand side, if you'll notice, each of these wires on the top of the solenoid have the current coming out of the page. And therefore, if I wrap my right-hand fingers in the direction of the green magnetic field lines, you'll see that that right-hand rule works. So I know that the right-hand side has a positive current. So the right-hand side says mu 0 times I enclosed. Well, what I'm going to do is if I know the total number of wires per unit length, which we'll call little l, then or which we'll call little n, excuse me, then the answer will be mu 0 times n. That's the number per unit length. Little n is equal to the total number divided by the length. And then I'm going to multiply that by the length, and that'll give me the total number of wires. And then I multiply that by the current, since the current's the same in all of them. So with that in mind, we can now set the left-hand side equal to the right-hand side. And when we do that, we get B times L is equal to mu 0 little n times L times I. And you see, of course, that the L's cancel out. And you just get that B, the magnetic field, is given by mu 0 times the length, or excuse me, times the number of turns per unit length times I. So B is equal to mu 0 n times I. If you wanted to, though, you could also say that would be equal to, let's say, B could be equal to mu 0 I times the total number of turns divided by the total length. So if you did that, then that's an acceptable expression as well. You just have to realize what the little n and the big N are. So little n is defined to be total number of loops divided by total length. I'll just make that length, not L. So length. And then big N is just the total number of wires, our number of loops. So using that version, we now have gotten two equations that are equivalent to each other, are one equation and one equation for a wire, current carrying wire. So we now have at least some sense of how to calculate, say, magnetic field strength due to certain configurations of current. I'm trying to make that B look a little nicer. Sorry about that. So there. All right. Now there's one more we might want to do, and that would be a toroid. You could actually do that. I'll show you what it would be. So if you imagine a solenoid that's real long and you curl it into a donut shape, it really would be a donut shape because it's basically a circle that forms a circle with its axis. So you can imagine it basically look like here's a circle, here's a loop of wire, here's a loop of wire, here's a loop of wire, but the whole thing is going to go around in a circle like that. And of course, on the inside, you'll have the other loop of wire, and it all goes around in a circle like that. That's called a toroid. Okay. And these current carrying wires, say on this side, are in fact pointing out the current's coming out of the page, and on this side in the middle, they're going into the page. Okay. So they continue around the edges all the way around. That would be a toroid. So you can imagine that the magnetic field lines would in fact be concentric circles. And in fact, the magnetic field would be basically a constant. Actually, I've got that direction drawn backwards. The magnetic field would be a constant essentially in that. And normally this distance right here from here to here is small compared to R, which is what I'll call this. Okay. So that's our plan. Now I'm going to draw the magnetic field lines in there. I'll draw them in green, and you can see because of this, the little coils on the top that are coming out of the page, the magnetic field is going to point that way around that one. And then of course, this one going in the page is actually going to point that way as well. So ultimately the magnetic field line for any distance R from the center, the magnetic field will be a constant. The magnetic field will be a constant. So if I again break this circle up into little delta L's, each little delta L will have the same amount of magnetic field strength associated with it. And that magnetic field will in fact be parallel to the wire, so that in Ampere's law, the left-hand side becomes summation B parallel delta L just becomes a fixed B at each place times delta L1 plus delta L2 plus dot, dot, dot for however many you do. In other words, we're going to get the same thing we did to this side. We're going to get for the wire that we got for the wire. So it's basically going to be B times 2 pi R. That's the actual distance around is 2 pi R. Now the right hand side, which is actually supposed to be mu 0 I enclosed, that's going to become mu 0 times the total number of turns. So that's N times the current in each wire, which is each one's the same. So now what I can say is that B times 2 pi R is equal to mu 0 times N times I. So we get B is equal to mu 0 n times I over 2 pi times the radius is the magnetic field for a toroid. So this is another formula you can use. Again, you don't have to derive this in an algebra-based physics class, in a college physics class, in other words. If you had a calculus-based physics class, they would make you derive it, but that's just another expression you can use to calculate a magnetic field, and that has to be basically the magnetic field within the little toroid. In other words, inside the donut. So I hope that helps. Have a good day. Let's stop sharing, and then I end my recording.